if you don't have the mass that's as a individual blob like the previous example, now your mass is the smooth continuous object. So you can use the definition of the previous part as well. So if you look after your XCM is come from sigma mixi divided by sigma m, right? So to do the summation like this, you can just have the infinitesimal of mass m in individual axis. This is the definition of integral through all different axes. What is this come from? For example, if you have the small mass over here and you have a distance away, to find the sigma mixi, this is another your mixi as well if you look in terms of comparisons, because this mass may be supposed to be over here with the small mass. So you have this mass with the position along x-axis like this, xi. You have xi multiplied with di, and you have another position mi, another xi. In this case, I will write over here, sorry, for example. So we have all of these along to complete this object. So this is the definition of integrals. So rather than you have the individual of xi dmi like this, and you sum up, the way to sum of this continuous example, you just use the integration part. So that's why this is exactly the same of the system of the particle, but you look into a smooth particle system. If you get a little bit confused, just remember the form of the integration like this. You have the total mass again and integrate x dm over here, so that you can find your xcm, ycm or zcm depend on the distance, whether it's x, y or z that you are about to integrate through the whole part. You can do integration as the coordinate, as we did in the previous example, or you can do it as a vector as well. If you have to identify the final vectors of the central of mass, as in terms of the positional vector. In this figure, it shows RCM as a positional vector. The delay is like this. It's come from the network, and I think the OBS and the WebEx system, they try to consume my RAMs and CPU. That's why some lagging happened. Sorry for this inconvenience. Now we look into this problem. So now we have the continuous mass with the densities. Lambda here represent the linear densities, which is the lambda is, you have the definition like a density, right? The normal density like D equal to M over V. However, this is with volume. The linear is what you looking after only a distance, not in 3 dimensions, only in 1 dimension. So for the linear density is equal to mass over the whole distance. So that if you look after only a small distance like this, it's also equal to small mass along this part divided by the small distance, which is this go to x direction. Now you would like to identify the central mass of this rod. Right, this one has mass m and length l. You would like to identify it, but since if the lot have the equality in the densities, the center of mass going to be at the middle of that rod. We will prove that by using our definition of the integration to find the XCM. So from the definition, we know to find XCM from this continuous mass, we have 1 over m integrate x dm. Now we look after this small particle as a dm, and x is a distance that away from the original position that we're gonna use this as a reference. So you have the definition of this term. Now you try to do some integration. However, you still have dm, and this is x. X is not a constant. X is variable. If you quantify dm on this part, x is quite short. If you quantify dm over here, dm not dx, x is quite lengthened. So the x is variable, and m it has some relation with dx over here. Since you have lambda equal to dm over dx, so that you can convert dm to lambda dx, and then you sub dm into this part. So finally you got xcm equal to 1 over m integrate x and multiply with lambda dx. Now lambda is a constant, since we state here is the definition of the density, which is the linear density of the mass over total length. This is a constant. You can take it off, so you have lambda over m integrate of x dx. So you would like to integrate from the original to the distance L, so you gone from 0 to L. So now you got lambda over m and x integrate x dx, you got x squared over 2, and you put the limit from 0 to L here. So you have lambda over m's, I got 2 outside, so you have L square minus 0 square in terms of substitute. So you can sub the lambda in as well, because lambda is m over L. So you have m over L and divide by 2m and multiply with L square. So you can see L can get rid of it and m can get rid of. You have xcm here equal to L over 2. To answer about the center of mass, the center of mass of xcm and ycm here is equal to L over 2 zeros. This is how you find the center of mass in this case. Right, we're going to the next part. Suppose this lot is non-uniform now. So what is mean by non-uniform? Rather than you have the lambda equal to m over L, this lambda is not uniform now. This lambda now become alpha x. So you still use the same definition, your dm by dx. Here, this can be a small m, sorry. So you can use this definition to rearrange the term that you did before. We also need to find the x coordinate of the center of mass in this case. So with the definition of the center of mass, xcm equal to 1 over m integrate x dm. Since the mass is not equally distributed, we also somehow find the relation of mass as well. We know mass is what we integrate from different small parts of the mass and sum it up together. So the definition of the mass now, you will have lambda dx in this term for the dm's. And your lambda now is integrate of alpha x dx, because the lambda is equal to alpha x over here for the non-uniform of the density. So this lambda relate to x in terms of alpha x. So by this, if you like to integrate for the overall, the total distance, so you find the total m here equal to alpha integrate of 0 to L x dx equal to alpha x squared over 2 0 to L, so it's alpha L squared over 2. This is your total mass of this system. Now we got the total mass, so we would like to identify integrate x dm here. So your integrate x dm, no, not x dx, sorry. Your integrate of x dm is equal to integrate of x, and your dm is your lambda dx, right? Which is alpha x dx. So this term, you will have the alpha outside, which is alpha is constant, and x squared dx, like this. So you integrate from 0 to L as well. So now you have this term after the integration as alpha L cubed over 3. You can try to rearrange this term, right? Is x third, which is cube over 3, and you sub L and 0 in, so finally you will get this. So in order to find xcm, now you just combine all the information together, 1 over m, 1 over m, and integrate with x dm here, which is equal to 1 over m is this part, is 1 over alpha L squared over 2, and multiply with this alpha L cubed over 3, and finally you will get xcm equal to 2 over 3 L, like this. This is how you use the information of the way to find the xcm if this mass is continuous but it's not uniform. Now, we did learn about finding the center of mass. We can use that information to explain how the system of the particle moving. This is an example of the swarming drone. If you see, this drone can be moving together. You can program it to be automated, to let it moving through the space, avoid the barriers or obstacles. So if you can determine whether, for example, like this one as a center of mass, this spot as a center of mass of the drone, you can determine how these 4 drone or whole drone moving with the velocity accelerations. If you know the velocity, you can find the momentums of the center of mass of this drone. If you know the acceleration, you can find the force that induce or exert to this drone system as well. This is the importance of the drone, and you know the total M is the big M. So you can use just P equal to mvcm. If you know the central mass, the momentum is represent momentum of the central mass. Also, the force that exert to the central mass is also equal to total mass that multiply with acceleration through the central mass. And now we can do any calculation that we learn on individual particle, and we assume this system of the particle have the mass or central of mass over there, and predicts how these object moving. Now, this is the part that I already stated. If you know the RCM. This RCM is your center of mass, right? In terms of the positional vectors. If you dip this RCM by dt, you will know the velocities. Or the definition, if you already learn about it, the RCM is equal to sigma MIRI divided by big M. If it's the velocity, it's also come from sigma MIVI as well. But this term, if you look carefully, MIVI, this is momentums. You can see the individual momentums, and you have this big M moving toward this side. This is the source of the momentums that you can see. The whole momentum still moving in the same direction of the center of mass. This is the total momentums. When we see these kind of resultant things, we will think about the conservation of momentums, right? Sigma Pi equal to sigma Pf. This is what we did learn. So that if you know the total momentum from initial moments, you can determine the resultant momentums in the final state. Not only the momentums, also the force of the system of the particle as well, if you know the center of mass. This is the definition that we state already. Now, this is kind of like an example of what is happened. Think about when this rocket launched from the Earth's surface, and this is a kind of prototype of the SpaceX shuttle. It was launched by like early date on 2014, and you can see when it's lift up, not like from the submarine, but it's from the land. From this figure, it's come out as a projectile and explode. While it explodes, it still carries some momentums and it's moving. Since you learned about the projectiles, if the object has the initial velocities and it was dragged from the due to the gravitational acceleration, this object moving as a projectile like this. However, if it's got exploded at some position and all the debris from this rocket like scatter around like this, the total, the net of the velocities or the momentum still moving in the same directions. This is your conservation of the momentums. You can trace the path of this object moving still in the same path of the projectile. Let's go through our first example. Not first now. This is the first example of the part of the system of many particles. The rocket is flying vertically from this case, and it have total mass, and it's reached the altitude at the speed of 300 meters per second. So maybe at this height, at 1,000 meters, it have the velocity, which is initial velocity, equal to 300 meters per second. This have the big M, I will write as a total mass. Afterward, it's got explosion at this point, and it's split into 3 parts with the same mass. So it's M over 3, M over 3, and M over 3. Which is one fragment is moving upward. So it's moving with 450 meters per second. How about another one? Another one moving eastward, right? Eastward is this direction. If I got, this is like north, down is south, this is east, this is west. Eastward, in 240 meter per second. So you would like to justify how about this one. How about the third one? What is their speed? What is this one? What is its speed? So to determine this is a kind like a conservation of momentum, right? You know, from the conservation of momentums, you use sigma pi equal to sigma pf. However, from that case, you just learn from a single particle and maybe knock to another one and have some conservation of momentums. Now we look into the system of the particle, which is it has its center of mass always at the same position. For example, in this case, so you can have mass m to represent the total mass, and sigma m is maybe breakthrough m1, m over 3, m over 3, m over 3 for another 3 fragments. So with the conservation of momentums, at the first event and the second event, from the first one you have mass m with the velocity zeros, which is, if you write it as a vector, it's going upward, so this one going to j direction, so it's plus j direction. And how about this one? This one going upwards as well in j direction. This is going eastward, so in I direction. We would like to determine this one. So now you got another 3. The first one is m over 3, 450 j. This is the first one. The second one is m over 3 here, 240 I. How about the third one? We would like to find it. M over 3 V3. You can sub this one in as well. So this is 300J. You can see M is can get rid of each other. So I get all M out. So you like to determine this. So I will rearrange the term. So you have V3 equal to, since this is all divided by 3, so I'll get it multiplied here. So it's 3 multiplied 300J and minus with 450J and also minus with 240I. So finally, you will find the V3, or the velocity of this particle of the rocket is kind of like a part of the debris of the particle moving in vector in form of this 240 I, sorry, how we write it, minus 240 I and plus 450J, because this is 900, right? And so in meter per second. This is how you can use the conservation of momentums for the calculation, and you know some basic understanding of the total of mass, which is you can represent the center of mass or the system of that object moving through the center of mass going in the same path. What is this explained? It's explained initially this rocket initially moving along this direction, and it had pi sigma p1 going this way direction. How about this one? You will see it when you sum it up. This sigma p also going in the upward direction as well. Sigma p2. And due to the conservation of momentum, sigma p1 equal to sigma p2.